Hello, welcome back. For this section, we're going to go through polynomial and rational inequalities. This can get a little confusing. We're going to start with polynomial inequalities, and I'm going to flash back to a previous video and talking about behaviors of graphs, polynomial graphs. So the instructions are, first we're going to move all the terms to one side, if they're not already. So we need a 0 on the right-hand side to be able to tell what we're doing here. We're going to factor, find the critical values, and I'll show you how to do that in a second. That's the zeros of the polynomial. Test the sign within each interval, and actually instead of doing that, I'm going to use the behavior that we learned earlier with that sheet I just showed you. And you're going to write your answer in interval notation. So let's jump right into it. So here we have a few inequalities, and for the first one, we have x cubed is bigger than 16x. Subtract the 16x over, so now I have the 0. What we're saying here is we want to know when this graph is bigger than 0 or positive. You can see we have a third degree polynomial here, and if I go back to my original behavior of what a graph is going to do, we can see that when it's an odd polynomial, degree polynomial, and it's bigger than 0, it's going to start down and end up. So you can see I've started down, and at the end I ended up. So what we're going to do is factor it completely, and then find the critical values. The critical values, or critical numbers in this case, are whatever make it equal to 0. So the critical values in this case are 0, -4, and +4. And I say, it looks like I'm saying opposite signs, but the +4 minus 4 gives me 0, -4 plus 4 gives me 0, and 0 times whatever gives me 0. And you can see we start down, and it comes up, then down, and then up again, and ends up. What we're getting from this is we want to know when this polynomial, or this polynomial, or this polynomial, it's the same one, is positive. When is it bigger than 0? We also don't want to know when it's equal to 0. Notice there's no equal symbol here. So when we write it in interval notation, we can see it's positive from -4 to 0, excluding the endpoints because there's no equal to. If it was here, we would have brackets here. Then it's negative again, so we don't want that. We only want where it's positive. And then it's positive from 4 to infinity, not including 4. Let's take a look at 2. 2, once again, is a x times x times x is going to be x cubed. That'll be the same as this one as far as shape goes. Starts negative, ends up positive. Now you'll notice this one is less than or equal to 0. So what we want to know is when this graph is negative, when it's less than 0, when it's below the x-axis. Here's our x-axis. Well, we know it starts down, comes up, crosses at -1. Here are critical values, -1, 5, and -3. We come up, hit the -3, cross back down at -1, and pass back up at 5. Now the point is we want to know when it's negative. So that's down here. That's -infinity to -3. Here we have a bracket because it's equal to. So -3 is okay here. It then goes positive, which we're not interested in for this one. Then it's negative again. So from -1 to 5, including -1 and 5, this should be a bracket, not a parenthesis. We are going to be positive, negative. We're below the x-axis. Let's move on to these next two examples. So for number 3 here, this is not factored, so I had to actually go through and factor it. It wants to know when it's less than or equal to 0. That's negative. So we want to know when this polynomial is below the x-axis, or when y is negative. We grab our critical values. That's going to be 0, -4, and +2. And once again, this is a cubic. This is a third degree polynomial, so it starts down and ends up, just like the previous two. Start down, we cross at -4. It's a negative there. -4 to 0 to 2, and ends up. Once again, they want to know when it's negative, so we're down here, -infinity to 4. When we hit 4, it should be -4. We're including -4 because of the equal symbol that we're keeping with that. It's also negative from 0, which we're including, up to 2. Our fourth one here is going to be a 4 fifth degree polynomial. So again, it's going to have the same general shape. It starts down, ends up. But because it's x to the fourth, we're going to bounce off of the x-axis. Notice we don't have an equal symbol, so it's going to bounce off, and then it's just going to simply cross at x equals 3. Here's our critical values here. This wants to know when the graph is negative. And this is not when it's negative. This should be here. So it's going to be negative from negative infinity to 0, and then union with 0 to 3, exclusive. We are not including it. Let's move on to inequalities. Now these get really funky. First thing, we're going to move everything to one side, just like we did with the previous ones. We're going to combine all like terms into one fractional expression or one rational expression. We're going to factor the numerator and denominator. Find the critical values. That's what makes both the numerator and denominator equal to 0. Then we're going to have to test a sign, SIGN, within each interval of the graph. And then we'll write an interval notation. And again, even if it's an equal to symbol like we have down here, we will never include what makes the denominator equal 0, even if it does say that. A tempting thing to do, which is not right, is to multiply both sides by the LCD. That is not right. And the reason is because when you have an inequality, when you multiply two sides, if it's negative, you change the direction of the inequality. When it's positive, you don't. And depending on the value of x, it could be either or. So what we have to do is just get everything with a 0 on one side. This one already is. And it looks like the x-intercept is going to be at -3. That's what makes the numerator equal 0. The denominator cannot be plus or minus 2. So plus or minus 2. Now these are our critical values. These are our game changers. So we're going to throw down -3, -2, and 2. And what we're going to do is we're going to test a value within each of these regions. So on this side, I'm testing -4. I plug in -4 up here, crank it out, and it ends up, I get 1/12, but I don't care about that as much as I care about the sign. It's a positive 1/12. So that means on the left side, everything's positive. Between -3 and -2, I test a value, and I didn't write them out here, but when you test those values, it's going to also be positive. Between -2 and 2, maybe 0. You can see when we plug in a 0 there. I'm going to get a 9 over a -4. That's going to be negative. And something bigger than 2, say x equals 3, when I plug it in, it ends up being a positive also. So what's our conclusion? Well, they want to know when we are bigger than or equal to 0, which means positive. We're looking for positive values, including 0 values. So -3 will be included, but once again, -2 and 2 definitely will not be. So where are we positive? Well, we can actually go from -infinity all the way up to -2. -infinity up to -2. Notice that's going to include all of this as well. That's positive or 0, so we're okay. We don't have to break it up there. Now, if it didn't say equal to, we would have to break that up and exclude -3, but we're clear on this one. From -2 to 2, we're out. But from 2 on, and notice it's an open circle or a parenthesis on both of these because, again, we can't use values that make us divide by 0, ever. Even with an equal symbol here, that only means that -3 is included. The -2 and 2 are not. And so we go from -infinity to -2, or from 2 to infinity, excluding the numbers that aren't even in the domain. So this would be our final answer here. I'm going to let you work that one out. I want to get to number 3 here. Here we are. So for number 3, notice we don't have our 0. So what I have to do is I have to subtract that 2 over, get a common denominator, and crank it all out into a single display. So now we have a rational with a 0 on one side, which is really what we need. Less than or equal to means we're looking for negatives. And we only have one critical value. That's going to be -4. And once again, x will never equal -4 no matter what. We have no zeros in this case. So I went ahead and tested a point to the left of -4, -5 in this case. We ended up with a positive value. A number to the right, say 0. You can see we end up with a -9/4. which means all the numbers on this side, all the y values on this side are going to be positive. So if we're looking for negative values, then what we need is we are going to have from from negative 4 to infinity are going to give us our negative values. So here's our answer here. This one's even more complicated, or looks more complicated. We have to subtract that over to get our 0, get a common denominator, and shuffle it together. So now we're here. Our critical values are going to be 7, 1, and negative 2. 7, 1, and negative 2. Again, our denominator can never equal these values. We have a strictly bigger than anyway, so we're looking for positive values only. Then we test a value less than negative 2, say negative 3, into here. Something between negative 2 and 1, like 0, we plug it in here, here, and here. We get negative values. Between 1 and 7, we plug it in here, say something like 2. Plug it here, here, and here. We get a positive value. And anything after 7, so say 10, we could plug here, here, and here. So you would test each of those. Either way, we're looking for positive values. Where are we positive? Well, it looks like from negative infinity to negative 2, which again, it can't equal negative 2, even if there was an equal symbol there. It's also positive from 1 to 7, exclusive of 1, mainly because of the denominator, but 7 is also excluded because, again, there's no equal symbol there. So that's our final answer there. I hope you found that helpful.